that we gave last time. Right. So don't forget. Right. Any questions with the homework so far? You need to get anything answered on the board? Nobody? Okay, so what we'll do, we'll continue with some examples of finding areas of shapes. We'll continue that today. Okay, so we'll look at some examples of how we could apply the formulae that we studied in the previous class, and that should enable you to attempt the homework, right, a little easier. And in the first example, we'd look at the shape here. Okay, what we are required to do is to find the area around the circle. That is the shaded area or the crosshatch area that I'm putting in now. Okay, this is the area that we are required to find, the crosshatched area. Now this shape on the board, even though it wasn't indicated in the diagram, it should be understood that those two lines are parallel lines. And if we have a four-sided shape like this, which is known as a quadrilateral, where we have one pair of parallel sides, which means that no matter how far you extend those two sides, they will not intersect, then this shape is called a trapezium, right? This shape here is called a trapezium. Right? And the shape inside is called a circle. So if we are to find the area that is shaded or crosshatched in this case, we would have to find the area of the trapezium ABCD, find the area of the circle, and subtract the area of the circle from the area of the trapezium. Right? And that will give you the crosshatch area. Now the area of a trapezium, so if you write area required, the area required could be found by saying the area of the trapezium right? Let's call the area required A. Let's call the area of the trapezium AT, right? And to find the area required, what we'd have to do is find the area of the trapezium and subtract from it the area of the circle. Let's call that AC, right? So we have smaller letters to work with. Instead of having to write area of trapezium over and area of circle over again, we could just use AT and AC and A. Now the area of any trapezium, could come here, the area of any trapezium is equal to a half times, open brackets, the sum of the parallel sides. So the parallel sides would be BC plus AD. Right? So the area of a trapezium is a half multiplied by the sum of the parallel sides times the perpendicular distance between them. Now, in this case, the perpendicular distance was given, I'll have to put it in, I didn't put it in as yet. The perpendicular distance was given in this drawing here. And that perpendicular distance was given as H, and H was equal to 16.5 centimeters. Okay? So we'd have to multiply this that we have written here by H to get the area of the trapezium. Again, the area of a trapezium is a half multiplied by, which is understood here, the sum of the parallel sides, which is this, by the perpendicular distance between the two parallel sides, which is H. Alright, and that will give us what we need to find. So if we put that in here now, let's see what happens. It'll be a half times BC will be 13.2 centimeters. So you're writing your 13.2 plus your AD, which will be 25.8 centimeters, multiplied by your H, which is your perpendicular height, which is 16.5. Right, 16.5 centimeters. That's your area of your trapezium. What is the area of your circle? Now we could work all of this out, right? And let's get a figure. Okay, so when you work this out, you'd get a figure of 321.75, and then you have to figure out the units. Now the units of length in this case is centimeters, right? So the unit of area, which is what we're working out here, the unit of area will be whatever the unit of length is, centimeters squared. Right? So we have the area of the trapezium as 321.75 centimeters squared. What about the area of the circle now? AC. Let's find the area of the circle. The area of the circle will be equal to pi r squared. Area of any circle is pi r squared. Now what we'll do, we'll use pi as 22 over 7, right? You could have chosen 3.142, you know, you could have chosen that as well. What we did was to use 22 over 7 Then we're going to multiply that by r squared. R in this case is the radius of the circle. What we have there is not a radius, we have a diameter, right? A diameter is when you have a line that goes straight through the center, touching 2 points on the circumference, as shown in that diagram there. That is not a radius, it's a diameter. And our equation calls for radius, so we have to be careful. So the radius will really be 8 divided by 2, because a radius is half of a diameter. It is from the center to any point on the circumference. So the radius will be half of 8, and we have to square it. So you square it. Having done that, you should find that AC, which is the area of the circle, works out to be 50.29 cm squared. That's what it will work out to be. 50.29 cm squared. But we are rounding that off correct to 2 decimal places. Okay, we did a little rounding off there to 2 decimal places. The next step, of course, would be to find A, which is AT minus AC, the area of the trapezium minus the area of the circle. So we write, therefore, the area that we require is AT minus AC, which will be equal to 321.75 take away 50.29, or minus 50.29. Okay? And when we work that out, we'll get 271.46. Again, to 2 decimal places. But remember, this is centimeters squared. Important to put in your unit. If you don't put in that unit, you will lose marks. Okay? So make sure and put in your units. And make sure you put in your accuracy. In this case, we did it to 2 decimal places. So you put to 2 decimal places. And that would be your final answer there. Okay, in this example, we are asked to find the area of the kite. And we are given the dimensions from A to this position here, let's call that O, and then from O to C. A to O was 4 centimeters, O to C 8 centimeters, E to O was 3 centimeters, and O to D was 3 centimeters as well. So what we'd have to use is the area of a kite, and the area of a kite is given by the equation a half multiplied by one diagonal, which we call D1, by the other diagonal D2, or a half times the product of their diagonals. So in this case, it would work out to be a half times D1. We could choose any one as D1. Let us choose one diagonal D1 to be A to C, right? A to C. So that will be 4 plus 8. To get that diagonal, we call that diagonal AC. Okay, this here will be AC. And then we'll work out the other diagonal, which will be from E to D. That will be D2. That will be 3 plus 3. Okay? So we just work on that now. So that will be a half multiplied by 8 and 4, 12. Multiplied by 3 and 3, 6. So a half of 12 by 6. And that will give us 36 cm squared. 36 cm squared. The diagonals, one diagonal is AC, the other diagonal is ED. So all we have to do is find AC, ED by adding up the respective lengths and then multiplying them together and finding a half of it, because the area of a kite is a half times the product of their diagonals. Okay, so in this question we were asked to find the area of the compound figure, and to find the area of the compound figure, what we do is we divide it into two pieces, a top part and a bottom part. The top part, if we call that A1, and the bottom part, if we call it A2, then the area of the top part we say is A1, the area of the bottom shape is A2. Now the area A1, which is the area of the square, is side multiplied by side, or side squared, which will be 5 multiplied by 5, which is 25 cm squared. Make sure you have your unit correct. So the area of the first part, the top part, is 25 cm squared. The area of the bottom shape, which is a rectangle, is A2, and that will be length multiplied by breadth, or length multiplied by width, which in this case is 7 centimeters by 2 centimeters, which works out to be 14 centimeters squared. 14 centimeters squared. Now, all the way along, we should really be putting centimeters. So this should really be like centimeters here, centimeters here, centimeters, centimeters, so that you have your units all the way through. Okay, so consistently, that is the way it should be done. Therefore, the required area of the compound figure would be equal to the two areas that we got added together, A1 plus A2, and that will be equal to 25 cm squared plus 14 cm squared, and that would work out to be 39 cm squared. Okay, so that would be for part 1. Part 2 is what we will get into now. And part 2, they ask us to find the perimeter of the compound figure. To get the perimeter of the compound figure, as we said, we would need to deduce all of the lengths around the shapes. And in order to deduce that, we say this is a square. So the opposite side to this side here would have a length of 5 centimeters as well. 5 centimeters as well. In this shape here, the opposite side to the 7 centimeters would have a length of 7 centimeters as well. If this is 2 centimeters from here to here, then on top here is 2 centimeters as well. So I'll write in that 2 centimeters. And the balance would be 5 centimeters, take away 2 centimeters, which would be 3 centimeters. In this case, we would just have to add the 3 to the entire summation of the lengths. But if we were to assume it was symmetrical, which is logical in this case, we could say that each of these positions or portions will be 1.5 centimeters each if we divide the 3 centimeters into 2 equal parts. So this would be 1.5 centimeters here, and this would be 1.5 centimeters here as well. So to get the perimeter, all we have to do is add up all of the lengths. So we just do that. And we say the perimeter, P, would be equal to, and we add up 5, 5, 5, plus 1.5, plus 7, plus 2, plus 7, plus 1.5. And that will give us our total perimeter. And when you add up all that, you'll get a perimeter of 34 centimeters. All right, and that will be the answer for the second part. Finish now? Janelle, finish? Okay. Okay, so we are looking at the circle, the sector, and the segment. In the first diagram, we are looking here at a circle. Now, in a circle, you would have a center, the center point, and the circle will be drawn right around that center point. Now, from the center point to B, or the center point to C, or the center point to A, or the center point to L, all of those distances are known as radii, right? One distance, for example, CB, that's a radius. CA, that's a radius. CL, radius. C, that look like CE, CD, CC. So let's say this is CE. That will also be a radius. Now, if we go straight through the center from A to B, that'll be 2 radii, which equates that diameter. That's why we have diameter at the bottom here. Because those 2 radii, once you go straight through the center, is known as a diameter. And the area of any circle is pi r squared. The next thing we look at is a situation where we cut a part of that circle out. And let's say that part of the circle we cut out was A, O, B, and let's put up here C, A, O, B, C. That what we created there, that shade that we created there, will be known as a sector. But because that is smaller part, that's called the minor sector. Okay? And a very common way to think of a sector is if you have a big pizza and you are taking a part of it or a piece of it, then the piece that you will be taking is a minor sector out. Okay? And what remains in that pizza, that will be the major sector. Now, it's very important to know how to get the areas of the sectors. And to get the areas of the sectors, the best way to remember it is to first of all remember what is the area of a circle. So you write that down, because remember this is related to a circle. So you write down pi r squared as the area of the circle. Right, so what you'd have to know is the area of the circle is pi r squared, and for the minor sector, think of it as just being the area of part of that circle. Okay, but what part do you allocate to the sector? And it's easy. All you have to do is relate it to the angle that the sector contains. Now in this sector, let's say this sector contains an angle theta. Then the fraction that this minor sector would occupy in relation to the whole area of the circle would easily be found by saying theta over whatever the total angle of a circle is. And the total angle of a circle is how much? 360 degrees. So the area of a sector could easily be found by remembering what the area of the circle is and then saying that this is a fraction of it. What fraction? Theta, which is the angle in the sector, or subtended by the radius of the sector, divided by 360. Okay? And that's how you find the area. If you have to do the major sector, you just use the angle that would be in the major sector. So let's say this angle here in the major sector, let's do it in a different color so you could follow it. Let's say that angle was another angle. Let's call it, let's look at this angle here, and let's call that angle alpha. Right? Alpha is just another Greek letter that you could use for angle. So if we had to get the area of the major sector, it'll be alpha now over 360. Whatever alpha it is, it might be 310 degrees, might be 250 degrees, no matter, whatever it is, you divide it by 360 and multiply that by pi r squared. Simple like that. Okay, that's how you'd get your areas. So we write here, this would be one area of the minor sector. And this one here would be the area of the major sector. Okay? Then the other thing we have to be aware of is how do we find the arc lengths? Arc lengths is another thing. Now what is an arc length? Well, if I had to find the arc length going from A to B, just going from this point to this point, then we would have to find a fraction of the circumference. Now, we didn't discuss circumference across here, so let's discuss it. The circumference of any circle is 2 pi r, right? So you have to learn that by heart as well. So if we come back here and we rewrite, the area of the circle was pi r squared, and the circumference of the circle C was equal to 2 pi r. So this relation will help us to find the arc lengths, because just like the area, it would be a portion of the circumference if we had to find the arc length. So if we wanted to find the arc length AB, let's say we wanted to find arc length AB, what would we say? We would say that is a portion of the entire circumference of this big circle. So you write down what the circumference of the big circle will be. It will be 2 pi r, like this. Good? And it'll be a fraction of that. So if it was the minor sector we were looking at and the minor arc length AB, all we'd have to do is use the same fraction, which would be theta over 360 degrees. Okay? And if you wanted to find the major arc length going around on the other side, it would have been alpha over 360 times 2 pi r. Okay? Next one. We're looking at segment now. How do you find the area of a segment? First of all, we have to establish what the segment is. The segment will be if we draw a chord, which is a line going straight across from one point on the circumference to another, like if we did it here. Right? That would be called a chord. This is a chord here. Right? When we draw that chord, we divide the sector into two parts. The first part on top is known as a segment. And the part below we resemble, we know what that is already. We encountered it before. It's called a triangle. Right? That's a triangle below there. But what's important about that triangle is that it's a particular type of triangle. Because if we know, let's say this is O, this is A, and this is B, and we know the length OA is equal to OB, then this triangle is a particular type called an isosceles triangle. That's an isosceles triangle because we have two lengths equal. This length here will be equal to this length. So I'll write it over isosceles triangle. Okay? And to find the area of the segment, what we'd have to do is to find the area of the sector and minus the area of the triangle from it. That's how we get the area of that segment. So if we wanted to get the area of the segment on top, right, which is this area here, all we do is say area of the segment will be equal to the area of the sector, take away the area or subtract the area of the triangle. Okay? And we know how to find the area of the sector, and we know how to find the area of any triangle. So therefore we could find the area of a segment. Okay, so in this question, we are given a circle, and we are asked to find certain things from that circle. The first thing they ask us to find is the area of the circle. Okay, so we are asked to find the area of the circle. And the area of a circle is pi r squared. The area of a circle is pi r squared. So to find the area of the circle, we could say area of the circle is equal to pi r squared. What are we going to use for pi? Well, we'll use 3.142. We can use 22 over 7, or we could use what the pi that is on your calculator. In this one, they had said in the question to take pi. In this one, they had said take pi to be equal to 3.142. So that's what we'll use for pi, 3.142. Right, so we'll use that here, 3.142. 3.142, we'll use that as pi, and we multiply by r squared. Now r in this case is 3.5. That's r. It's the distance from the center to any point on the circumference, so we'll use 3.5 and we square that. Okay, if you go into your calculator and you type in that and you work it out, you'll get a figure of 38.4895. And if we round that off to one decimal place, you'll get 38.5 cm squared. Right? Don't forget that your area will be a length unit squared. Right? So you get 38.5 cm squared, and that'll be to one decimal place. So you write to one decimal place. Okay, so that will be for the area of the circle. The next thing that they were interested in is to find the area of the minor sector POQR. Now the area of the minor sector POQR will be, if you go from P all the way over to Q, but it's actually POQR. So you go P to O to Q and back through R to P. So that will be the minor sector that they're interested in. Now what I said to you, the minor area of the minor sector will be just part of the area of the entire circle. So you always write down to get the area of the minor sector POQR, all right, POQR here, right? To get that area, we consider the whole circle, which is pi r squared. But then we know it's just part of it. And the part is always found as a fraction of the whole circle. And the whole circle is 360 degrees. So it will be some fraction of that. The fraction of that will be the angle that is inside the sector, which is 45 degrees. So all we do is put 45 over 360 and multiply by whatever the entire circle was, which is pi r squared. So all we'd have to do is to work that out. Okay? And we could work that out simply by using what we had gotten before. Now remember, we had gotten pi r squared on top here, which was 38.4895. So all we'll have to do is 45 over 360 by 38.4895, and we'll get the answer. So 48 over 360 multiplied by 38.4895. There's a reason I didn't use the rounded off value, because I know it... Sorry. 45. Right, it's not 48, it's 45 on top. So we have to correct that. Thank you. So that's 45 over 360 by 38.4895. And if we calculate that, we'll get a much more accurate answer than if we had used the 38.5 rounded off. So once you calculate that, you'll get a figure of, if you round it off to one decimal place, you'll get 4.8 cm squared. So I write 4.8 cm squared, and again that will be to one decimal place. Okay? So that will be for the minor sector POQR. Then the next one will be the triangle POQ. Now the triangle POQ could actually be worked in more than one way. Right? The triangle POQ, you could actually work that using two equations. In this example, we will use one equation and we use the simpler one. In the exam, you'll go for the simpler option. And the equation that we will use is equation a half area of the triangle POQ. We'll use the equation a half AB sine C, where A and B are the lengths of any two sides and C is the angle included by those two sides. Now in this triangle here, POQ, right, if I draw that triangle across to show you what I'm talking about, that triangle there, POQ, what we realize is that one side is 3.5 centimeters, but the other side will also be 3.5 centimeters. The reason is that it's a radius of a circle, and the radii of a circle, all of them are equal. Good? So it means then that we have two sides, PO and OQ in a triangle, and we have the included angle between the two. So therefore we could use this equation because A and B represents the length of any two sides, and C is the angle included by those two sides. So therefore we could easily put in now a half multiplied by the length of one side, which is 3.5 centimeters, by the length of another side, 3.5 centimeters again on the other side, and we multiply that by sine of the angle included, which is sine of 45. Sine 45 degrees. And if you work that out, you will get a figure of 4 centimeters squared if you go to the nearest centimeter squared. Okay, so you would have got from 4 centimeters squared to the nearest centimeter squared if you had worked it out. The next one was the minor segment, the area of the minor segment PQR. Okay, how do you find the area of the minor segment? How do you find the area of the minor segment? Now the minor segment, I'm going to shade it out here now, is this. That's the minor segment. Okay? The minor segment could be found by taking the area of the sector and subtracting from it the area of the triangle. Okay? That's what we learned before. So the minor segment, PQR, which is what I just shaded out there, could be found by saying the area of the triangle minus the area of the sector. And that could be found by saying, what was the area of the triangle that we got from before? The area of the triangle was 4. So you write down 4. And we're going to take away from that the area of the sector, which we had found before as, sorry, we actually do need the reverse. It's supposed to be the area of the sector minus the area of the triangle, because the sector is larger. So let me take that, fix it here. All right. So the area of the minor segment is the area of the sector, and the area of the sector in this case was POQR minus the area of the triangle POQ. Okay? And we know that the area of the triangle, the sector POQR was 4.8 cm squared. And the area of the triangle POQ was 4 centimeters squared. So therefore, when we take the difference, we'll get 0.8 cm squared. Right, 0.8 cm squared as the area of the segment, the minor segment that you're interested in. Okay, so the next one we're looking at is the circumference of the circle. The circumference of the circle, which we'll call C, is given by 2 pi r. Right, we learned that, so you write 2 pi r. And 2 pi r, we're going to use pi as, we shall use pi as 3.142. So it'll be 2 multiplied by 3.142 multiplied by r. And in this case, r was 3.5 centimeters. Okay, and everything, of course, here is in centimeters. So it works out now to be, when we work that out, 2 by 3.142 by 3.5, that will give us a figure of 21.994 centimeters. And if we round that off to 1 decimal place, you'll get approximately, or to the, sorry, to 1 decimal place, you'll get 22.0 centimeters. Okay, so if you round it off to 1 decimal place, you'll get 22.0 centimeters to 1 decimal place. The last one is the length of the minor arc PQ. The length of the minor arc PQ. And to get the length of the minor arc PQ, all we have to do is recall that the length of the minor arc is a fraction of the length of the whole circumference. Same thing as we did for the area. So if I want to get the length of the minor arc PQ, I'd have to remember the length of the circumference, or what the circumference will be 2 pi r. And I have to remember that that minor arc would have a fraction, or be a fraction of that. What fraction? It will be 45 out of 360. So we use the same fraction, 45 out of 360 multiplied by 2 pi r. 45 by 360 multiplied by 2 pi r will be equal to 2 pi r. We got it already. Look, 2 pi r here. That is the circumference. We got that as 22 or 21.994 exactly. So what we do is say 45 over 360 multiplied by 21.994. Okay? And if you do 45 over 360 by 21.994, you'll get 2.749 centimeters, or 2.7 to 1 decimal place. Okay? So this works out to be 2.749 centimeters, or if you want to round it to 1 decimal place, it'll be 2.7 centimeters. If you want to round it off to 1 decimal place, so that'll be to 1 decimal place. Okay. So now you should be in a better position to work on the calculations that I gave you. So I expect you to work on them for the next